Hello and welcome. In this video, we're going to take a look at one of the more important interpretations of the definite integral. And we'll come up with just sort of a generic form for that kind of application that we call the net change theorem. Now, this all comes kind of from the combination of the definition of what the definite integral is in terms of like an area problem, as well as the fundamental theorem of calculus. So let's take a look at a little bit of theory and come up with this net change theorem. So remember, by definition, the definite integral of a function f from a to b is equal to the limit as n goes to infinity of this Riemann sum, the sum from I equals 1 to n of f of xi star times delta x. Remember, delta x can be calculated as taking b minus a as our interval width, dividing it up into n equal subintervals. Xi are the endpoints of each of those intervals. So from I equals 0, 1, 2 up to n, we can calculate those endpoints as a plus I times delta x. Xi star is just any sample point in each of those intervals. So for each of the n intervals, xi star is some number between the left endpoint xi minus 1 and the right endpoint xi. Now, by the fundamental theorem of calculus, we found that we can evaluate that without using limits and sums as just being capital F of b minus capital F of a, which is the antiderivative or an antiderivative of f evaluated at the endpoints. So in other words, f prime of x has to equal f of x. Okay, so what happens if I were to integrate a function that represents a physical quantity's rate of change? Let's think of an example. So let's suppose we have f of t, and I'm going to use t here to represent time. Let's say that that's the rate of flow of water into a pool, and that would be a rate of change of volume. So we might measure that in something like liters per minute. And this is a function of time, so that's the flow rate of water at t minutes for t greater than or equal to 0. Okay, well, let's start thinking about what we could do with a definite integral over an interval. Now, since t is my variable, this would be the definite integral of the function f of t from 0 to 10 with respect to t. Okay, well, let's take a look here at the definition of that definite integral. Well, just changing a variable, but this would give me the function f evaluated at ti star times delta t. Now, if we want to think about the units of this, remember that this function, that's representing the rate of change of volume, so this would be in liters per minute. And we're going to be multiplying that rate by a short subinterval, delta t, and we can say that that's going to be measured in minutes. So we're taking a rate of change of volume per minute and multiplying that by a width of time, or an interval of time in minutes. This will get us a small amount of volume that has now flowed into the pool. So this would equal the number of liters of water that flows into the pool during each of those little subintervals. So subinterval 1, we get a small amount of water flowing in, subinterval 2, subinterval 3, all the way up to subinterval n. Now that would end up, if we sum all that up, that would be the total amount of water that flows into the pool during that time interval. This gives us the total amount of water that has flowed into the pool for the time interval from 0 to 10. So it doesn't actually tell us how much water is in there if there was water to begin with. It's just the total amount of water that has changed over that time interval. We call that the net change. This is the net change in volume over that interval of time. It might make a little more sense if this is a rate of change of volume to call it v prime of t instead of f of t. And then let's take a look at that and see how the fundamental theorem of calculus might just give us another interpretation of it. So let's say v prime of t is equal to the rate of flow of water into a pool in liters per minute at t minutes. Okay, well, we can integrate that. Let's say we just pick any time interval, maybe from 0 to 20 minutes. Now we're going to integrate v prime of t, and rather than thinking about the definition, we can think about the fundamental theorem of calculus. We need an antiderivative of v prime of t, and then evaluate the endpoints. We need something whose derivative is v prime of t. Well, that's pretty easy because v of t is a function that is the antiderivative of v prime of t. And we're going to evaluate that from 0 to 20. And you can see that this is just equal to the volume after 20 minutes minus the initial volume at 0 minutes. So really, this is a net change in volume. This is just thinking like delta V. It's a change in volume over that time interval. It's taking what we are going to be at with our final volume am subtracting our initial volume to get a net change. So the net change theorem, put quite simply, it just says that the definite integral of a rate of change over an interval from a to b is the net change from a to b. The definite integral of f prime of x from x equals a to x equals b is simply just f of b minus f of a. So if you think about it, any physical quantity where we know its rate of change, by integrating over an interval, we'll figure out the net change. Now, net change you have to be a little bit careful of here because there are certain quantities that we want to be always positive versus some quantities we're okay with being negative or even zero. So an example might be displacement is a net change in your position. And you could travel all around the world, but if you come back to where you started, we would say your net change in position is zero. So the rest of your trip is just not even accounted for. Whereas distance, that's a whole other matter. So let's just think about where you might have to be a little bit careful about making that differentiation between net change and that total that you're looking for. Okay, here I've got a graph of a velocity function. Let's say this is the velocity of a car. Now, you can see I have a positive velocity, 4 meters per second for the first 4 seconds, and then, well, my velocity drops down to 0. So that must be that I'm coming to a stop. And you can see that I'm stopped for 2 seconds, and it looks like I put my car in reverse here, and I start getting some acceleration in a negative direction, negative velocity, and that's only for 1 second. And then, well, very quickly, it looks like I start accelerating forward again. So maybe I've got a manual in transmission, and even while I'm reversing, I just put it into first gear and start driving forward. And you can see I don't really stop for any duration of time here. I just quickly get to 0 velocity and then positive velocity. Now, if I start integrating this, we can start taking a look at different time intervals and see what happens. So maybe for our first example, what if we were to just integrate this for the first 4 seconds? So integrating from 0 to 4 of this velocity function, I could shade that area in so I can represent that. That shaded area right there, if you take a look at it, that's taking really just the area of a rectangle with a height of 4 meters per second and a width of 4 seconds. So 4 times 4, that will be 16 meters per second times seconds. And that'll get me meters. So I've traveled a displacement of 16 meters. I've also traveled a distance of 16 meters. All right, that's a fairly straightforward calculation. Now, what if I were to start integrating over this entire duration for all 11 seconds? Changing this to 11, I need to go and have more forward traveling motion from 4 to 5 seconds, and that is going to get me extra displacement. You can see that that's just a triangle. That's an additional 1 second, a height of 4, so then an area of 2 meters. Now I've traveled 18 meters. But then as I start including from 5 to 7, nothing important happens. There's no area between the function and the t-axis. Then I start including this area from t equals 7 to t equals about 9.5 here. And this area has a negative velocity. And so that means I'm going to be traveling backwards. My displacement will be negative, and I'll be subtracting the green area from the blue area to get my net change. And then I'll have to include positive displacement from about 9.5 to 11. So in the end here, if you were to label these as areas, area we can just think of as being positive. A1, A2, and A3, if area is always just a positive value, then the net change of displacement from 0 to 11 seconds, this is graphically interpreted as A1 being positive displacement, A2 being a negative displacement, and A3 being positive displacement. So in the end, it looks like I'll overall have traveled forward more than I've traveled backwards because I have a lot more blue area than green area. But you can also imagine, depending on the function, it is possible for your net change to end up being 0. Now, what if you wanted to end up with distance? And I just wanted the total distance that my car has traveled. So you got to remember that the odometer on your car doesn't just spin backwards if you put the car in reverse, right? It's going to keep ticking forward. There's no hope that you can try to reverse that by driving in reverse all day. It's going to start adding up your odometer. Well, if you want distance, you're going to have to make sure that you treat every one of these areas as positive. So remember, the interpretation here is taking the definite integral of velocity over time interval is displacement. And if you want something to always be positive, we need an absolute value. In order to get distance, we need to integrate the absolute value of v of t. That can be a little bit tricky to actually do in practice. You have to remember one of our properties for definite integrals. It's pretty easy to calculate it if the function is continuous and we can find its antiderivative. But what if the function is not continuous, or if it has little jumps or something? As soon as you start getting absolute value signs in there, it's maybe better to think about your function as being a piecewise function where pieces of it need to be flipped so that it ends up being positive. Pieces don't need to be flipped if they're already positive. If that's the case, then we can use the property of definite integrals that we can split up our interval from a to b into a to c and c to b. So for example, in this case, if I wanted distance, rather than having to worry about how I handle this absolute value sign, let's just take a look at the separate little intervals where I would have to make an adjustment of sign. From t equals 0 to 5, doesn't look like I need to make any adjustments at all. That is already traveling forward, and that's going to get me distance, which should be positive. But actually, from 5 to 7, there's no velocity, so there would be no change in distance or displacement there. I just have to maybe integrate from 7 to 9.5 very carefully. What I'll do is I'll integrate from 7 to 9.5 of b of t with a negative sign in front, which will flip it and make it above the t-axis when I integrate, and that'll give me a positive value. And then from 9.5 up to 11, it would appear that my velocity is already positive, and I don't have to worry about whether or not I get a positive or negative value. It'll end up being positive displacement or distance. So there you go. So that's the basic idea. If you wanted to find the total change instead of the net change, so if you want distance instead of displacement, you just have to be kind of careful about analyzing the function, figuring out where the function is negative, and then for those intervals where the function is negative, change the sign of the function, and then just add up a bunch of definite integrals where you've made sure that the function is positive in each of those little intervals. So hopefully that gives you at least a little new interpretation of where definite integrals are useful. That area problem we're talking about, if you think about the kind of graph you're working with, and you think about the units of the vertical axis and the units of the horizontal axis, you multiply those two things together, that'll give you the units for each little block of area on your graph. So meters per second times seconds, each little block, every unit of area there is going to be in terms of meters, which makes sense that it's displacement then. And you can apply that to liters per minute multiplied by minutes will get you the number of liters. So that area problem becomes much more relevant when you make it a physical quantity that's changing with respect to some other quantity. And we'll take a look at that in other videos. Thanks for watching, and I'll see you in the next video.